common practice in my area for installing ground electrodes is to bury them approximately 6 inches below the surface of the ground. This is usually done before landscaping or sod is installed. In my opinion, the requirement to bury the grounding electrode conductor at least 12 inches below grade is not necessary. The purpose of the grounding electrode conductor is to provide a low resistance path to ground for fault currents. As long as the grounding electrode conductor is in good contact with the earth, its effectiveness will not be significantly reduced by being buried at a shallow depth. It is important to understand the function of the grounding electrode system and its components within the overall electrical system. The grounding electrode system is designed to provide a connection to earth, offering a low impedance path for fault current to return to the source. This path facilitates the operation of overcurrent protective devices, such as circuit breakers and fuses, which are intended to clear ground faults quickly and safely. The grounding electrode conductor, often referred to as the GEC, is the conductor that connects the service equipment, the separately derived system, or other electrical systems to the grounding electrode. Grounding electrodes can take various forms, including ground rods, ground plates, metal underground water pipes, and concrete encased electrodes, also known as UFERs. The selection and installation of grounding electrodes must adhere to the requirements outlined in Article 250 of the National Electrical Code, or NEC. These requirements ensure that the grounding electrode system is effective in providing a low impedance path to ground. When installing a grounding electrode system, several factors must be considered. Firstly, the type of grounding electrode must be appropriate for the soil conditions and the specific application. For example, in areas with high soil resistivity, multiple ground rods may be required to achieve the desired low impedance to ground. Secondly, the size of the grounding electrode conductor must be adequate to carry the available fault current. The NEC provides tables and guidelines for determining the appropriate size of the grounding electrode conductor based on the size of the service entrance conductors. Thirdly, the grounding electrode conductor must be properly connected to the grounding electrode and the service equipment. These connections must be made using approved methods and materials to ensure a reliable and low impedance connection. The depth at which a grounding electrode conductor is buried can impact its effectiveness. While the NEC does not specify a minimum burial depth for the grounding electrode conductor itself, it does specify requirements for the depth at which grounding electrodes, such as ground rods, must be installed. For example, ground rods must be driven into the earth to a depth of at least 8 feet unless rock bottom is encountered. In such cases, the ground rod can be buried at an angle not exceeding 45 degrees from the vertical, or it can be buried in a trench at least 30 inches deep. The purpose of these requirements is to ensure that the grounding electrode is in contact with a sufficient amount of earth to provide a low impedance path to ground. The connection of the grounding electrode conductor to the grounding electrode is a critical aspect of the grounding system. This connection must be made using methods and materials approved for the purpose. Common methods include exothermic welding, listed pressure connectors, and irreversible compression connectors. The connection must be mechanically strong and corrosion resistant to ensure a reliable and long-lasting connection. The grounding electrode conductor must be securely fastened to the grounding electrode in the service equipment. This can be achieved using clamps, straps, or other approved methods. The grounding electrode conductor must be protected from physical damage. This can be achieved by routing the conductor through conduit or other protective enclosures. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. It is important to consult these tables to ensure that the grounding electrode conductor is adequately sized for the application. The material of the grounding electrode conductor is typically copper or aluminum. Copper is the preferred material due to its high conductivity and corrosion resistance. However, aluminum is also permitted, provided that it is properly sized and protected from corrosion. The grounding electrode conductor must be continuous and without splices or joints. This ensures that the grounding electrode conductor provides a low impedance path to ground. If a splice or joint is unavoidable, it must be made using an approved method, such as exothermic welding or listed compression connectors. The grounding electrode conductor must be installed in a manner that minimizes the risk of damage. This can be achieved by routing the conductor through conduit or other protective enclosures. The grounding electrode conductor must be protected from physical damage, corrosion, and other environmental factors that could degrade its performance. The grounding electrode conductor must be inspected regularly to ensure that it is in good condition and that it is properly connected to the grounding electrode and the service equipment. Any damage or corrosion must be repaired promptly to maintain the integrity of the grounding system. The grounding electrode conductor plays a vital role in the overall safety and performance of the electrical system. By providing a low impedance path to ground, the grounding electrode conductor helps to protect people and equipment from electrical shock and fire hazards. It is essential to follow the requirements of the NEC and other applicable standards when installing and maintaining grounding electrode conductors to ensure that they function properly and effectively. The grounding electrode system serves several crucial functions. Firstly, it limits the voltage rise on electrical equipment during ground fault conditions, reducing the risk of electric shock. Secondly, it provides a path for fault current to flow back to the source, allowing overcurrent protective devices to operate and clear the fault. Thirdly, it helps to stabilize the voltage to ground, minimizing electrical noise and improving the performance of sensitive electronic equipment. In addition to the NEC requirements, there may be local codes or regulations that govern the installation of grounding electrode systems. It is important to consult with local authorities to ensure that the installation meets all applicable requirements. Proper grounding is essential for electrical safety and equipment protection. A properly installed and maintained grounding electrode system provides a low impedance path for fault current to flow back to the source, allowing overcurrent protective devices to operate and clear the fault. This helps to prevent electrical shock, fire, and equipment damage. Therefore, it is important to understand the principles of grounding and to follow the requirements of the NEC and other applicable standards when installing and maintaining grounding electrode systems. Remember to always prioritize safety when working with electrical systems. If you are not comfortable working with electricity, consult with a qualified electrician. Working with electricity can be dangerous, and it is important to take all necessary precautions to prevent injury or death. The grounding electrode system is a critical component of the overall electrical system, and it is essential to ensure that it is properly installed and maintained. The grounding electrode conductor, as the link between the electrical system and the earth, plays a vital role in providing a safe and reliable path for fault current. Understanding the requirements of the NEC and following best practices for installation and maintenance are essential for ensuring the effectiveness of the grounding electrode system.